Welcome to a new lecture of aerodynamics. We continue our discussion of the potential flow theory and how we can use it to predict the aerodynamic load on a surface. So today we are going to discuss the source panel method, which is a numerical method that allows us to compute the pressure distribution around a non-lifting aerofoil. So we have this aerofoil that is in a free stream, and what we do is we solve the Laplace equation, which is the del square phi and del square psi, to get the velocity around this shape of the aerofoil. And so this is the big picture, and eventually we get the velocity from the potential flow solution, from the velocity potential. And once we get the velocity, we compute the velocity field and compute the velocity magnitude on each point on the airfoil. Remember, there's the no-slip condition does not exist in the potential flow theory. And then we can use Bernoulli to find the body pressure, the pressure on the surface pressure on the airfoil, given the free stream velocity far away upstream of the airfoil. And this V body is what the potential flow theory that we get. It's the velocity on the surface of the airfoil. So the method starts with let's say, proposing the shape of the airfoil. So that's a given. And from there you work out your way around to get the streamlines, and from the streamlines you get the velocity distribution, and then you get the particular velocity on the surface, and from the velocity on the surface you get the pressure, and from the pressure you get the loading distribution. So in the details we will see this in more clearly as we move further on in this lecture, towards the end of this lecture. As we try to solve for the velocity on the surface of the airfoil, a necessary step is to apply a boundary condition that is associated with solving the Laplace equations. And that boundary condition tells us that the surface of the airfoil is a streamline. So once it's a streamline, by definition it does not have any velocity perpendicular to the streamline. So that's the n velocity, the n unit vector, the normal to the surface of the airfoil, and the velocity along the normal has to be 0. That's one of the boundary conditions that we set, which means that the only velocity on the surface of the airfoil can only be tangential. It can be 0, but it cannot be normal. It can be the only possibility for it is to be tangential. So this is the description that tells us that there can be no normal velocity perpendicular to any point on the airfoil or on our object that we're studying, and the velocity is related to the velocity potential. So the velocity vector is related to the velocity potential according to the d phi dx and d phi dy, which you can plug in here, and eventually it tells you that which comes back to the point which we have seen before, is that the velocity potential lines are perpendicular to the streamlines, and since the surface of the airfoil is a streamline, then we can set the condition to be we can rewrite this condition as that there is no normal velocity perpendicular to the airfoil, is that the gradient of the velocity potential function along the normal direction is 0. So this is a constant velocity potential line. These are the red lines are all constant velocity potential lines. And we can write something similar in terms of the stream function, is that the stream function on the surface is also a constant. So this is a constant stream. That streamline is a constant value of the stream function. And here we write that the velocity vector is tangent to the surface of the airfoil. So that's the surface of the airfoil and the velocity vector are tangent to each other. So the method that we're going to talk about today is the source panel method. And what comes handy here is the source term, the singularity that we have introduced in the past, and we can write it in terms of velocity, the velocity potential, and the stream function as so. So let's look at the velocity potential. That's what we're going to see next. So this is the main item we're going to use in the source panel method. And in the source panel method that we're going to introduce today, we're only going to deal with non-lifting surfaces. So if we're dealing with an airfoil, it's going to have a 0 angle of attack, so it wouldn't, and it's symmetric, and it doesn't have a net pressure differential perpendicular to the velocity, free stream velocity, i.e. there is no lift. So as we said, this is our velocity potential function for a source / sink. So a sink, you'll have a minus sign, or the lambda itself, the strength of the source, is going to be negative for a sink. So to remind you, a source is a singular point at the origin from which the velocity vectors issue, or the streamlines also issue in a radial manner, and the velocity potential lines are tangent, are perpendicular to the stream function, which means that they are circles. So you can see that the velocity potential. So we're going to define a sheet AB or a surface AB, and we're going to break it into elementary sheets. So we're going to break it into small pieces, and we can look at it from a side view, and then we're going to break that surface into those tiny bits. S is the coordinate system along the surface, and ds is just an elementary piece of this surface, is an elementary length along the S direction. So the lambda is going to be distributed over the surface, this length ds, and the velocity potential, or the contribution of this length of the what we call the source panel, or the source sheet, is going to be lambda ds, as you can see here. It's the lambda, and then the rest is the same as we've seen before for the singular point source, 2 pi natural logarithm of r. So now what we want to do is to consider a point somewhere in the flow. So here we have a sheet, and along that sheet we've put sources and sinks along it, such that they are distributed over each bit of the surface AB, and the lambda can vary over the whole length S. So it can be strong here, it can be stronger at certain locations and weaker at other locations. So if now I want to compute at any point in the flow, so an arbitrary point P, which is designated by its coordinates x and y. If I want to compute what is the contribution of this elementary panel, it's a single panel of length ds, what is the velocity potential contribution? That would be d phi. So it depends on the distance between the center of the panel and between the point P, which is the r. So that gives me the contribution of this bit of the panel to the velocity potential here. And then if, due to superposition, because our velocity, potential flow solutions are, or the potential flow equation is linear, so the different solutions also act linearly. So you need to get the net velocity potential at point P. You need to sum up or integrate the effects from each one of those ds's. So you have sheet AB infinitely broken into an infinite number of ds, and then you just sum up the effect at point P. So that's the, so if we have a surface AB and we want what we want to eventually generate is a streamline that looks exactly like point AB, and what we do is we distribute an infinite number of or a distribution of sources and sinks along that line, such that in the end AB would also be a streamline. This S direction is also a streamline, so that the velocity is only parallel to that line, is tangent to line AB along the S direction. So that's what it is in a nutshell. So the sheet element, so here just to summarize, the sheet element is of length ds, and its strength is lambda times ds. So the velocity potential contribution at point P is d phi, so as we have seen in the previous slide. And now if I want the phi from all the elements along AB, you just sum them up, which means you integrate them, the lambda ds over 2 pi log r from point A to point B. So that's the, and then that, if I pick my lambdas just right, my lambda distribution over the surface S just right, I'm going to get the shape that I started with. I'm going to get the shape of AB. So our task in the potential flow theory is to find the lambda that is going to give me AB to be a streamline. So if I want to study an aerodynamic body, let's say I have a new design for an aerodynamic body, such as so, I'm going to distribute a sheet of sources and sinks, a distribution of sources and sinks all over the surface, and put that in a free stream. And if I get my, if I select my lambdas, the distributed strength of the source of each panel just right, I'm actually going to get I'm going to get a streamline that looks exactly the same shape as the body that I started with in this particular free stream velocity. And that because a streamline, I'm going to get streamlines inside and streamlines outside, but I'm particularly interested in this closed loop streamline because by definition, because it would also resemble a solid body in terms of mass, because a streamline cannot have velocity perpendicular to it. And you see that's the boundary condition that we have set all along to give us this streamline. So that's where the boundary condition we discussed moments ago comes into play, that it helps us generate a streamline. that has the same shape as the body that we started with. So the story becomes is what is this distribution lambda of this? So now to get this, so that's what the point of the workings of the potential flow theory, or the source panel method, which is part of the potential flow theory, is to find this distribution lambda that gives us the shape that we started with. And what we're going to make a couple of assumptions, is that over a single panel, if I take this as a panel, that lambda is constant. It doesn't vary between point A and point B. So let's say, so I've taken my surface, which is I start with, and I break it into panels. So panel A, panel B, panel C. Over a single panel, the lambda is constant, but between panel 1 and panel 2 and panel 3, the lambda, the strength of the source can vary. And then I'm going to take the midpoint of, I'm going to call it the midpoint of a panel, and I'm going to call it the control point. So if this is my surface, I've broken it as you see into panels. The midpoint of each panel I'm going to call the control point, and that's where I'm going to put the lambda times the length of the panel. That's the strength of my panel. So I'm going to use this control point to measure distances to this particular panel. I'm not going to do the integrate. I'm going to compute the distances relative to the control point of the panel. So that gives us a more manageable way of doing the integration. So as we will see in the next slide. So here's the setup of our problem. This is what a potential flow, what a source panel method problem looks like. What you're given, or what you start with, is you're given the surface of the object, or this is the surface that you are particularly interested in. So that we know, we start with this a priori, and the question, and then that surface, that object, is placed in a free stream of velocity v infinity, where that's the velocity far away from the object, and the pressure far away is also p infinity. We need to point that out. And we might have an angle between the chord line and the free stream velocity. So this we could have, so you'll see that free stream velocity if is parallel to this line. So that's the free stream direction. So we want to keep that in mind as we move further on. So I start with the surface of my with a given geometry, and then what I do is I'm also given a free stream velocity. Then what I do is I start by breaking my surface into not an infinite number of panels, but actually a manageable number of panels, and a good number is probably between 50 and 100. So I break my my surface into straight pieces of panels, and at the center of each panel there is the control point. And my task is I'm placing a distributed source along each panel, but the source strength between panel 1 and panel 2 can be different, but on the same panel itself the source strength is a constant. So this is the setup of the problem. Then what do we do next with those panels? So here's what we do next. Let's look at what's happening. So I have a panel here, and that panel has panel J has a strength of lambda J, and that panel contributes to any point in the flow, some arbitrary point x and y, It contributes velocity, it contributes a stream function, and it contributes a velocity potential function. So it contributes all those at this particular point. But also each one of the other panels will do the same thing. But let's focus on the jth panel. So if P is an arbitrary point, it has coordinates x and y. So we have to define the origin of our coordinate system. It has to be well defined. And then that delta phi that this panel J is going to produce at point P, we can compute it from the distance between panel J and point P. So that's the radial distance from P to J. And just like we've seen in the previous slide, that contribution is just the strength of the panel, length of the panel J, so the strength of the panel J, length of the panel J, and 2 pi, and then the distance times the logarithm of the distance between point P and the panel J. So let's move ahead, and as we've said that the lambda is constant, it doesn't vary over ds, so I can just actually take it outside the integral. So I don't have to do the integral because lambda is constant. I just multiply, and I use the distance r between point P and panel J to be the distance between the control point and the control point of panel J and the arbitrary point P. So I've taken the lambda outside the integral, and then if I want, so that's the contribution, that delta phi is the contribution of one panel to this point. If I want to find what is the phi at point P, what is the magnitude of the velocity potential, or what is my u component of the velocity, or what is my v component of the velocity, or what is my stream function at point P, so all these are at point P, they all follow the same procedure. So what we're going to do is we're just only going to look at the velocity potential. So the velocity potential, each panel J contributes a delta phi here. So I then have to sum them all up. I'll have to sum up all those delta phi j's, the contributions from each panel to the point P. So you sum them all up, you get the velocity potential function at point P, and as I said, you can do the same story for each one of the others, but we're sticking with the velocity potential function. So when you sum all the delta phi's, so you plug in the log RPI ds, and then you have the lambda over 2 pi. So you just sum them all up for all panels from 1 to n. So that's panel 1 here, panel 2 is also contributing, panel 3 is contributing, panel J is contributing, so you'll complete the circuit, and you get the phi. And as we said, the distance is between the point P, which we're interested in finding what the velocity potential at, that's point P, and so that's the xp and yp, and between any panel that we are considering at the moment right here, so panel between 1 and n, so panel J. Okay, so then if I now take, so that's all good if I'm interested in what's happening in the free stream. If I want to know what the velocity potential at this free stream, or what the velocity in the free stream is, then that's all good and fine. But we still don't know what our lambdas are. So for that, why don't we find the lambdas first, and then we can compute whatever we want, where we want it. So for us to compute the lambdas, let us not consider point P in the free stream, but actually let's consider the control point of panel I. So that's what we want to do. Let's consider the the control point of panel I. And you see where we're heading with this. What we want to do is we want to compute the contribution. We want to see. We want to say what is the velocity potential function at panel I due to the all the panels as well as the free stream that came here that we are subjected to, the v infinity. It also contributes a velocity potential. Or in other words, if you want it more simply, we are saying what is the velocity components, the u and the v, the horizontal and vertical velocity components of the velocity vector at point I, and to do that we need to sum up the velocity contributions. So this panel gives a velocity, contributes a velocity to control point I, and this panel contributes, and the free stream velocity also contributes a velocity component to the control point I. And what I will end up with is the velocity in terms of all the strengths of these panels. And what I do next is also go get the effect on the other panels. So I'm going to end up with, because the lambda is unknown, I'm going to end up with an n number of equations that describe the velocity at each panel from the contribution of each from every other panel as well as the free stream. And then we will be able to apply our boundary condition, which is the d phi dn to be equal to 0, as we have seen in the first slide in this lecture. So this is where we're heading. That's why we're looking at point I. And same story as we have done for an arbitrary point P in the free stream. So that's not at point P, it's point I. But that's the induced delta phi at point I. So this is point I, I'm sorry here. Due to the jth panel is going to be so now I compute the delta phi j, so you can get it from the previous slide, and then I sum them all up. So that is the delta phi j is what I have in this square, and the total phi at point for the control point I is just the summation of all the contributions of the panels from panel 1 to panel n, including the panel effect on itself. And the distance, as you see, is the distance for each j here is the distance between my panel I. So this is R. Let's call this panel 1, R1, I. And let's call this panel 5. That distance will be R5, I. So you get the idea. It's the distance between the panel I'm considering and the panel I'm considering, the control point that I'm considering, and every other panel on the body that I started with. But can you recognize a problem here when I is equal to j? When I is equal to j, the distance between the control point and the center of the panel itself is actually 0, so you're going to end up with log of the 0. And if you go back to our source panel, you can actually get the limit to find that the effect of the panel on itself is just lambda over 2. So we'll come to that in a second. But these are the coordinates of the so we have xi and yi and xj and yj as we just explained them. So xi and yi is actually the receiver panel, and so that's the receiver panel or the receiver control point. Let's stick with that nomenclature. and xj, yj is the giver, is what is the one that's contributing. So all of them will be givers, and this will be receivers, and then we'll repeat the computation for each one of those, for each control point, for each control point of each panel on this body. So now we're looking at panel I. So this is panel I, which is receiving the effect from all other n panels. So n minus 1, including itself, will be the n panels. All other panels are n minus 1, and when you include its effect on itself, then it'll be, the total number would be n panels acting on this control point. So now we need to apply the boundary condition, and the boundary condition will be, as we said, is that we want this to be a streamline, so the velocity perpendicular in the normal vector direction, the unit n vector direction is going to be 0. The velocity is going to be 0, or d phi dn is 0, as we have seen earlier. So we're talking about the same thing, v dot n. The velocity vi, the velocity at panel I, the velocity component in the perpendicular direction to the panel will be 0, which means the d phi of panel I, which we have actually computed right here, so that's the phi at panel I, will the d phi dn at panel I will actually be equal to 0. So as we've just said that in the previous slide, that phi has n panel contributors, as well as it has the v infinity contributor, the free stream. So we'll have this extra term when we're computing the normal velocity. So we have the component of the normal velocity. So if I want to compute the v normal on panel I, so let's call it v normal on panel I, will be equal to the contribution of all n. So here I should use a capital N to mean normal. The small n refers to the n number of panels, the contribution of each one of the n number of panels, and the contribution of the v infinity in the normal direction. So the normal contribution of the n number of panels, if you will, so as not to confuse you too much here. And then if we look at the normal contribution of the v infinity, we look at the tangent, which is parallel to the panel. So the tangent of the panel is just the line, and the direction of the v infinity, as we've seen in the previous slide, or in a previous slide, maybe a couple of slides ago, it's v infinity. So v infinity dot the normal will be actually the cosine beta right here between the normal vector to the panel itself and the v infinity. So that's the easy part. The v normal, as we've seen, is just the to get the v normal, we need to get this thing d phi dn to be 0, and we computed the phi from in the previous slide, which is the contribution of each one of the panels. But now we also mentioned the issue of the effect when I is equal to j. So we have to deal with that now. And when I is equal to j, the contribution will be lambda over 2. And when I is not equal to j, so here that's j is I is not equal to j. So all the other panels, so this should be I. So let's just get rid of that. I is not equal to j. Not equal to j. So this is the effect of the other panels on the particular control point. What this is actually a, so then I sum them up, v infinity plus vn, and it gives me this, and I equate it to 0, and it gives me this particular equation. So that's, we get the effect of the panel on itself, we get the effect of the n-1 panels on panel I, and then we get the contribution of the free stream on panel I, and we equate that to 0. So that gives us the eventually will give us, you'll see I have here 1 to n, so I have an n number of equations, and they're all linear equations because lambda, I only have lambda I and lambda j. So I get an n number of linear equations with the unknowns being the lambdas, n number of lambdas, so for lambda 1 to n, and then I can solve them using any linear system of equation solution methodology, very basic. And then I have my lambdas. So what do I do with those? So I get those lambdas as a solution. So I'll find what the strength of panel J, panel 5, panel 1, panel 2. So that will come out. Then what do I do with those? So we now did the hard part, and now comes the easy part, is what do we do with them? Well, for one, so we've already found them. We can find the velocity, and we'd expect the velocity to be parallel at the panel. We can find the parallel velocity at each panel. We expect, when we check our solution, we expect that if we compute the velocity perpendicular to any of the panels, we expect it to be 0. So that would be one sanity check on, so that should be equal to 0, that should be equal to 0, and that would be a sanity check on our solution that we didn't make a mistake in our code. Then I compute, so how do I compute this velocity component on panel I? You compute the contribution that is of the v infinity, that is, so that's v infinity is parallel to this direction. I compute the contribution parallel to the panel itself from v infinity, as well as all the parallel or the tangential contribution of all other panels. So that gives me the velocity at each one of those control points along my surface or my contour line. And then once we have this, remember we looked at this before, I can compute the pressure coefficient just by, well, effectively what we're doing is we're taking a streamline, the divider streamline, we're taking point infinity where the pressure is P infinity and the velocity is V infinity, between that point and any point on the body. So when you take Bernoulli between point A and point B, which is any point on, or point I, any point on the body, the pressure coefficient will be just 1 minus VI over V infinity square, as we've seen in a previous lecture. So that gives me my pressure coefficient. So I now have my pressure distribution around my object, and then I can get the loading, I can get where the center of pressure for the top surface, or for this particular element, or for this particular piece of my of the object that I'm studying. So I can get I can get the effect, the forces, net forces, and so on. Well, you want to remember that the source panel method that we're introducing here assumes that we're going to have a zero angle of attack and that our flow is symmetric. So we're not going to be dealing with any lift generating flow. For that we need, as we've seen in the Kutta-Tsiolkovsky theorem, that we need some circulation to get us some lift, and also as we have seen in the circular cylinder. But that we will not cover. It is a little bit more involved than the source panel method, at least. But here, at least, you can get an idea of what the methodology looks like. And as we said, as a sanity check, you compute the normal velocity to any panel, and you should get it to be 0. And we can write that as the summation of lambda j sj for all panels to be 0, which is mass conservation for our aerofoil or our aerodynamic shape. So this is pretty much the source panel method. Is one, you start, let's say you have the geometry of the body, that's what you start with. You break it into panels, these little pieces, and then you distribute. You don't have to have an infinite number, but you distribute a number of sources. Sources, we mean by a source and a sink is the same thing, but it has a minus sign over the panels. So you put distributed system of sources and sinks over all these panels that you have here, and then you solve for the lambdas. Each source will have a strength lambda. You solve for this lambda, the strength, and once you found the strength, you compute the velocity, and from the velocity you get the pressure coefficient, and you get the then you can use it to get the aerodynamic loading on the object. Okay, so let's put this into practice. So I have a Matlab code here, which I will actually share with you and copy. So what it is, we're going to use this Matlab code to look at the flow around a circular cylinder, a symmetric flow around a circular cylinder, non-lifting flow. So we already have a simple a simple solution from the summation of a doublet with a uniform flow to give us the flow around a circular cylinder. So this would be our sanity check for the solution that we're going to get. And remember, when we did a doublet and a uniform flow, we got the pressure coefficient to have a relationship with the angular position on the surface of the cylinder. So theta equals 0, theta equals, so the U infinity comes in this manner. This is theta equals 0, theta equal pi over 2, theta equal pi, and theta equal 270 degrees over here. And what you'll notice is that these are our two stagnation points, and we have a CP of 1, and where the streamlines get squeezed the most, so they get too tight together, you get the maximum velocity and you get the minimum pressure of minus 3 at theta equal 90 degrees and minus 90 degrees. So this would be our sanity check. Will the velocity of will the source panel method, the numerical method, give us the expected answer? So let's go and run this Matlab code. So here we're doing it for a circular cylinder as a check. And first thing is we're defining the circle. So here you define your body, but if you have, the circle is easy to define. It's just defined by its theta locations and x and y locations. But if you have a more complex shape, maybe you want to import that, you might have a different type of equation here. So this xy definition of the locations of the panels is going to differ. So here I'm defining the body and I'm also defining the panels. And then I get the control points on the panels, and I compute the length of each panel. So I've broken now my object into n number of panels, and here I have I'm doing the steps of 22.5 over 2, so maybe I'm doing maybe 8 or 16 panels. So you have 360 as a circle. So then I get my control points, and then I get the length of my panel, and I get the contribution I get the contribution of the or the slope of the panel. That's the angle phi, and then you can do some plotting to make sure that you're getting the right shape that you thought you were putting in. And eventually this is where you set up your linear system of equations for the source panels. And this is taken right out of the book of Anderson. He has the terms A, B, C, D, and S and E. And then you apply your boundary condition of the normal velocity to be 0 at each panel, and then you solve the linear system of equation. So that's what linear solve is the command in Matlab to solve a linear system of equations, and then you end up with the solution, which is your lambda. That's the strength of each source and sink term, and then we'll do some plotting. So let's run this, so that I'm sharing with you. So when you run it, so let's look at each one of those figures. First one is the CP. So here's the CP. I'm plotting the x, y. So I'm getting my circle, and the red dots that you see here are my control points. And you'll see, so for this, let's look at the stagnation point right here. So the points are actually shifted a little bit. The labels are shifted from the points. So this is my stagnation point, so it has a CP of 1. And same thing here, this is my stagnation point, it has a CP of 1. So that makes sense. And then I look at 90 degrees, at theta equal 90 degrees, and I get my pressure coefficient to be -3, and theta equal -90, and I get the same thing. So that's actually the same as I got from, or what we'd expect from the singular solutions that we have done before. Very good. And then you can plot the pressure coefficient as a function of the angle theta, and you'll get the same picture that we were expecting. CP goes between -3 and +1, the stagnation point. And you can count how many we have between theta equal -180 to +180. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 32 points in this solution, and it gets it really, really nicely. And then that's CP. So then you look at the labels of lambda over 2 pi. We can label them, and you can see that the panels on the front actually are all sources because they are positive, and the top and bottom panels at theta equals 0, pi over 2 and -pi over 2 have a strength of 0, and then the panels that are downstream are actually sinks, so they're all negative in magnitude, and the stronger panels are actually the ones at theta equals 0. The weaker one is at theta equal closer to 90. And here, that's just the labeling of the angles, just to make sure we're so that's your 90, that's your 0, that's your -180, and that's your -90. So I will, and this is the angle that the free stream makes, the angle phi that the free stream makes with, so here let's just look at what that is. So here's your angle phi that we looked at before. It's the slope of the panel with the horizontal, and the free stream is the horizontal too, so that's the phi, and you'll see that this panel is 0 degrees, and this, let's just and the panel at the front is actually 90, so it's all making sense. So that is the source panel code that we have, and we'll just summarize some of the results that we get. So when I use 8 panels, as I have here, I'm not getting a smooth curve for the pressure coefficient, but I'm actually getting the values at the important thetas 0 and pi over 2 and so on to be the same as what my solution got me. So these are the panels that I had, 8 panels. But if and then you label them, and you see that these ones are actually sources and the ones downstream are sinks, which is consistent with what we have seen when we were doing the Rankine oval and the semi-infinite Rankine oval. So when we closed the semi-infinite Rankine oval we needed to add a sink of the same magnitude as the source. So it's all consistent with each other. But now once you do more panels, like 32, you're going to get the shape just right. You're going to get the right shape for what the CP equal 1 minus 4 sine square theta. You're going to get the stagnation point of CP1 and the minimum pressure of CP minus 3. So this concludes the source panel method, and in the coming lecture this also concludes the potential flow theory, or that's what we want to cover in this course, as much as we want to cover the potential flow theory in this course. And moving forward, we will start looking at how reality can be different from, and how reality can be similar to what the potential flow theory predicts. So this would be the material for the coming lectures. Thank you for your attention, and I will be talking to you soon.